In this video, we will talk about Kepler's laws. We will explain the first law that describes the motion of planets around Sun in elliptical orbits. We will then talk about the second law that is associated with angular momentum of the planets that's going around the Sun. This is followed by the third law that describes the relation between the orbital period of the planet and the radius of the orbit of the planet that's going around the Sun. Finally, we will solve a few problems to illustrate some of these concepts. In this diagram, you have a planet that is moving around a Sun here in an elliptical orbit. This F and that F are the foci of this elliptical orbit. Kepler's first law simply states each planet moves in an elliptical orbit with the Sun at one focus of the ellipse. So in this case, the Sun is located exactly at the focus point on the left. So that is Kepler's first law. Kepler's second law essentially is a law concerning areas and therefore angular momentum, as we shall see shortly. The upper figure here shows a planet with mass m moves around in an elliptical orbit around that Sun. As the planet moves from point 1 to point 2 in a time interval of delta t, this line, the green line that connects the Sun and the planet, will sweep out a certain amount of area. Let's call it A. We can shade that area in the following manner. So that is the area A, swept out by that green line as the planet moves from point 1 to point 2 in a time interval of delta t. Then, as the lower figure shows, the planet will get to point 3 and it will move all the way to point 4. And in doing so, it will also trace out a certain amount of area in the same time interval. Now that area is shaded region right here. Kepler's second law says the shaded region that is being swept out in the same time interval delta t is also A. So formally, Kepler's second law simply states a line from the Sun to each planet, in this case the green line shown there or here, sweeps out equal areas in equal times. So if that green line sweeps out equal areas in equal time intervals, then we can write the time rate of change of area being swept out is a constant. We also know from geometry that if you have a slice like that, let's call that angle theta and radius r, then this area of that pi is given by half square of the radius times the angle in radian. Substituting this expression inside that derivative, we get the following equation that says the time derivative of half r squared theta is a constant. Of course, if we assume the points 1 and 2 are very close together, or 3 and 4 are very close together, so that any variation in r can be neglected, and the term half r squared can be taken out of that time derivative to give us half r squared d theta dt, and we know that is constant. But we know that d theta dt is quite simply the angular speed of this planet around the Sun. Thus we can write the following. We also remember that for a particle moving around in an orbit like that, its angular momentum is given as mr squared, which is essentially the moment of inertia, times the angular speed. So by substituting r squared omega as angular momentum over mass inside this equation, we find the left-hand side of this equation can be written quite simply as the angular momentum over 2 times the mass of the planet. The entire term is a constant. Since mass is a constant, we are forced to conclude that the angular momentum for this planet is also constant as it revolves around the Sun in an elliptical orbit. So what that means is the angular momentum L is indeed conserved. So Kepler's second law is equivalent to the law of conservation of angular momentum. Finally, let's look at Kepler's third law, a law that relates the orbital period to the radius of the orbit. Now, for simplicity, we shall begin this analysis with circular orbit, as shown here. For a planet with mass m that is moving with a uniform speed of v around this central object, let's call it a Sun with mass capital M, we know the uniform speed can be written in the following manner. The circumference of the orbit, 2 pi r, where r is the radius of the orbit, over the period of the orbit. Taking the square of this expression, we get v squared equals 4 pi squared r squared over t squared. As we have seen before, since this planet with mass little m is moving in a circular orbit, the centripetal force that it experiences is provided by the gravitational attraction from the central object with mass capital M. And we can write this expression as g, product of the two masses over the separation distance squared, equals the centripetal force on that little mass as little mass times the uniform speed squared over the radius of the orbit. The little m will get cancelled, and you have cancellation of the r, and that will enable us to express the v squared in terms of the other three variables as follows. So we have v squared equals gm over r. Equating these two expressions, we have the following result, which can then be rearranged in the following form. T squared equals 4 pi squared over gm times r cubed. So this is an important expression which says the square of the period of any planet is proportional to the cube of the radius of the orbit. And this applies for circular orbits. This result is known as Kepler's third law. Note the proportionality constant is dependent on the mass of the central object, this mass right there. So this proportionality, which is essentially Kepler's third law, has interesting implications. This figure here shows two planets, the red one and the white one, orbiting around the central object with mass capital M in circular orbits. The red planet has an orbital period of t2 and orbital radius of r2. The white planet has an orbital period of t1 and orbit radius of r1. So let's assume that they orbit in that direction around the central object with mass capital M. Since they are orbiting around a common central object, and this proportionality suggests for the white planet, and likewise this equation for the red planet, we see that since they orbit around the common object, the right hand side of these two equations are the same, so we can equate the left hand side to each other, giving us this important result. So if we know, let's say, the orbital period of the white planet, and we know its orbit radius, and we know the orbit radius of the red planet, we can figure out the orbital period of the red planet from this equation. What if the orbit is an elliptical orbit? In this case, we have to replace the radius of the orbit with the length of semi-major axis, namely a. So in this case, the expression would read as follows. The square of the period of this planet equals 4 pi squared over g times the mass of this object there times the cube of that semi-major axis A. So for elliptical orbits, the Kepler's third law reads as follows. The square of the period of any planet is proportional to the cube of the semi-major axis of its orbit. Let's do a problem. Planet Mercury has an orbital period of 88 days and orbit radius of 5.8 times 10 to the power 10 meters. If a hypothetical planet orbiting the Sun, just like Mercury, has an orbital period of 60 days, what is the radius of its orbit? Since both these planets are orbiting around the common object, which is the Sun, we can compare the orbital periods and the orbit radius in a following manner. M stands for Mercury and P is the unknown planet. Since the orbital period for Mercury is 88 days, so that's 88 squared, the radius is 5.8 times 10 to the power 10, cube of that, equals the orbital period of the hypothetical planet is 60 days, so that is 60 squared over the radius of that hypothetical planet that we want to find. So solving this, we can get the radius for the hypothetical planet as 4.5 times 10 to the power 10 meters. And that solves the problem. Note that we did not have to change days to seconds because the periods appear on both sides of the equation and the common conversion factor will just cancel out. Problem 2. A satellite of planet X travels in a circular orbit with radius 9 times 10 to the power 6 meters. Its orbital period is 8 hours. Determine the mass of planet X, the central planet. So we use the familiar expression t squared equals 4 pi squared over gravitational constant times the mass of the planet X, which we want to determine, times the orbit radius cube. Since we know the period is 8 hours, but we have to change that to seconds, so that is 3600, since 1 hour has 3600 seconds in it, equals 4 pi squared over g is 6.67 times 10 to the power minus 11 times the mass of planet X, which we want to determine. The orbital radius is 9 times 10 to the power 6, cube that, and we can solve for the mass of planet X, and that will be 5.2 times 10 to the power 23 kg. And that solves the problem. Thank you for watching.